Unfortunately, in the main, these structures are not homogeneous. So you get BOPT, PE structures, BOPET, PE, foil PE, BOPP, PE, just to name but a few. And so that makes it very difficult or almost impossible to recycle after use to any value resin stock because you have such a mixture of materials there. And there is a move to homogeneous structures. And this is being driven by major global companies. They don't want the asymmetry in the packaging. So certain companies are saying they don't want polyester in their structures anymore because it inhibits their ability, if they've got an overthinnic structure, to recycle it. So some of the new structures that are being talked about and looked at are HDPE laminations, heat stable BOPP to replace polyester against CPP, so all polypropylene. And even the polyester companies are switching on to this because they know their business is under threat. So they're working out what they can do to eliminate the needs for, say, CPP or PE in structures. So they're working on heat sealability and improving the heat sealability of their products. Once you get to homogeneous structures, it makes it easy to recycle if you can separate, and I'll touch on that a little bit later in this presentation. So what about foil and the barrier it provides? Can it be replaced? You know, there's so many structures out there still that have aluminium foil in them. And Liam touched on the fact that we've worked with a number of companies. And one of the major areas that keeps coming up is, how do I get foil out of my structure? Two reasons for that. It prevents recycling, but it also inhibits incineration, which a lot of countries are doing with their packaging waste. If you've got all this aluminium foil in your structure, you end up with a big lump of aluminium in the bottom of your incinerator once you've burnt it. So foil is a big no-no, and all the major fast consumer moving products groups are looking at trying to get this out of their structures wherever they can. Here's an example, typical example of a foil structure used quite often for sachets, for dried products. The BOPET on the outside could be paper, and we know things like soup packets and things like that are paper PE, foil PE. Well, that could be changed. And here's an option, and it's an option that I'm currently looking at with a major player, global player, and that's to replace the BOPET with a heat stable BOPP, include a barrier coating that gives performance close to foil, and then replacing the PE on the inside with cast polypropylene. So what you actually have in that structure is you have 99% polypropylene and a little bit of barrier coating, probably about 1 gram per square meter, that doesn't inhibit the ability to recycle that product. Can you replace foil? Why not? Some people believe foil is the ultimate barrier. But what we actually find is it's not quite what people think, because there's been a drive to go thinner and thinner on the foil, which is driven by commodity prices. Aluminium goes up and down, and shortages and all those good things. And as you go thinner and thinner, there is more chance of rupture. There is also more chance of pinhole. So in fact, the foil is not a continuous membrane. Add to that the issues of processing foil at converters. How many times in a converter has there been a slight nick on the edge of the foil, and of course it won't run. So you can end up with huge amounts of waste. And many applications that use foil no longer do so. For instance, coffee. Coffee at one time was a structure that included foil. Very, very few companies now use foil in their structures. And if you look at something that possibly could have had foil in it at one time, but didn't, is if you look at your Walker's crisp packet, that's got vacuum deposited aluminium in it, and that provides a very high barrier to both oxygen and moisture. So yes, foil can be replaced. And it's belt and braces. Often foil is in the structure because that was what was around at the time. And people don't really question, do I need that absolute barrier that a nice thick layer of foil would provide? And the answer is, in a lot of cases, no, you don't need that. But you have to have a will and a commitment to push the barriers to see if you can replace the foil and if that gives you enough barrier for the product being packed. And barrier coatings have improved, and in a lot of cases have the answers. How do barrier coatings improve sustainability? Once you have homogeneous structures, the coating is typically less than 1 gram per meter square. As I've said, don't compromise recycling. And quite often, the weight of the coating is less than that of the ink. Some of the types of coatings that can be used, and I've put the old favourite there, PVDC, because it's been used for many, many years. Although it's losing credibility, and environmental impact of PVDC is not great in some markets, particularly in Europe, frown upon its use. But you've got vacuum deposited aluminium, vacuum deposited aluminium oxide, vacuum deposited silicon oxide. In fact, that is quite an expensive product, and not very many suppliers of that. You also have vacuum deposited aluminium with new technologies, and steaming down the track, there are new novel coatings and additives that will provide you barrier. So what I thought it would be interesting to do was to actually show you what some of these barrier coatings do to films in terms of improving the barrier of those films. So if you look at a standard polyester film, moisture barrier of 16 to 20, and oxygen barrier 31 to 93. And don't take these as tablets of stone. You go to lots of people's websites, and they all quote slightly different figures and slightly different conditions for testing. But in the main, they give you the flavour for what you can achieve. So you put some aluminium, traditional vacuum deposited aluminium, onto the film, and you lower the MVTR to 0.3 and the OTR to 0.45. You can put an alox on, which is clear and is used extensively in retort packaging for reheating the microwave, and you see the improvement that you get. And then with vacuum deposited Cyox, you get an incredibly big improvement, and the best on the chart there for addition of that. But it is very expensive, and it also has to be top coated to prevent damage to it, as is normally the case with alox. Standard BOPP with vacuum deposited aluminium, you know, big improvement in moisture barrier from 5.5 to 0.15, but polypropylene inherently does not have an oxygen barrier, so by putting the aluminium on there, you're taking it down to less than 20. And with vacuum deposited alox, you also see a massive improvement. Lots of people have concerns when using vacuum deposited coatings for barrier, and it all revolves around barrier integrity. You know, you've got a piece of foil in a structure and it looks very good. You know, if it's got anything major wrong with it, like holes in that, it will tear in lamination. So you have a high degree of comfort factor. So consistency of application of the deposited coating is high in everybody's mind. And lamination bond strength, very important. How well is that coating sticking to the film that it's being applied to? And if it's not sticking very well, then there's a fair chance that your lamination will start to delaminate, and particularly for bigger packs, that really does become an issue. And this is the one that also always causes worry. These coatings are quite fragile. When you unwind the roll, you may have high points where you have anti-block agglomerates in the film, and you will get pick. And then if you had a film that's got a lot of these picks, you would hold it up to the light and you would get a starry night effect where lots of pinholes in the vacuum deposited coating. And what that does is it is a great detriment to the barrier. Then you get physical damage, scratches and scuffs where the coating is removed. And again, that will significantly cause a deterioration in the barrier. So we have new vacuum coating technologies, and just like to thank Nick Copeland for having a discussion with him recently about their new Alabond and Dark Night technology. Basically, the Alabond enhances coated adhesion, and it does that by introducing a sealing layer for the coating to bond onto. And very important, it densifies the aluminium coating. And that means that the aluminium atoms are more closely packed, and so there are less interstitial spaces between them. And so there's less room for vapors, whether it be water or oxygen, to pass through. And as a consequence of that, the barrier improvement is also enhanced by an increase in surface polarity, which means it's more susceptible to inks and adhesives. And that in turn enhances the lamination bond strength and also reduces the risk of coating pick because the coating is more tightly bound. The Dark Night technology they use is to ensure that the freshly coated film does not come into contact with rollers, which would abrade the film agglomerates. Like in a polypropylene film, that would most likely be anti-block, and leaving voids in the coated surface, thus ensuring a continuous barrier of coating. There is another technology for vacuum deposition, and that's in vacuum chamber coating. There are not, to my knowledge, there are only 2 suppliers globally at the moment that have this available to them. And this technology allows the vapor deposited coating to be immediately coated actually inside the vacuum chamber. And you say, well, it can't be a liquid coating. No, it's not. It's a coating that's applied and then it's either hit with electron beam or plasma to cross-link that coating. And that coating then acts as a sacrificial layer, preventing physical damage or coating pick. And it also locks coating and agglomerates in place. So if you have an agglomerate on the film that may have been susceptible to being pulled off when the roll is unwound, it can't, because this coating locks it into place. So what I thought I'd do then is actually show you how these new technologies improve the barrier. So if we look at the first one, which is Alabond on barrier of BOPP at an optical density of about 2.8, you see you end up with an MVTR of 0.03 and 5.12 for oxygen. And you look at that, and that's remarkable when you consider probably the most available on the market. You're looking at 0.4, so a dramatic improvement in moisture barrier and a 75% reduction in oxygen transmission rate, which is very, very significant. And that then takes you into the realm of foil and the barriers that foil can offer, particularly in the case of MVTR. And CPP, you might decide that you're going to put a 2-layer structure together, and you want CPP as your sealant layer. So here's some information on the effect of Alabond on CPP. Again, a dramatic improvement in the moisture barrier, and an even bigger improvement than on BOPP for the oxygen barrier. And when you look at what it's come from, that is remarkable. And certainly a CPP with that sort of level in a BOPP laminate structure would give you very, very good barrier and almost close to foil performance. If foil was absolutely pristine, which we know in reality that there's an operating window and sometimes it's not quite where it should be. And the effect of in-vacuum chamber coating on barrier BOPP, it's optical density of 2.8. Again, a halving of the moisture barrier and reducing the oxygen barrier by over 66%. And for BOPP, again, you're getting similar figures as what you would with the effective Alubon. As I said, there's only 2 suppliers of this in the world. One of those does market it quite readily, and believe it or not, made a lot of the polyester. It's being used in industrial uses at the moment. The only one caveat with this is because it's using 2 oligomers in the coating procedure, some slight questions about what's left. Do you fully polymerize and cross-link it? Are there any monomers left which could compromise its food contact? In discussions with one of the suppliers of this material, they think not, and I know they do have approvals for this material. So we have new traditional coating technologies steaming down the track. I'm currently working on a coating that's been developed, and it's providing an initial OTR of 5 cc's per meter squared per day. And this is the initial start point. And we believe that we can get very, very much higher than that level. Sorry, lower than that level in terms of transmission, but higher in terms of barrier. Just to give you some details about this one, those figures were derived after it was applied to a 50 micron LLDPE. The coating is water-based and gravure applied. Dry coating weight of about 1 gram per square meter. There is absolutely no chlorine in this material. And we believe that increased coating weight is likely to further increase the barrier. And it is currently being developed to replace foil when used for a gas barrier in packaging. And the final thing is the coating is actually heat sealable as well. And on top of that, there are additives being produced currently by some companies, and these will actually be extruded at the time of film manufacture and make the substrate multifunctional in terms of barrier without damaging the recyclability credentials. Wouldn't it be lovely that if you could just put an additive into, say, a cast polypropylene film, and you immediately enhance the barrier 10 times? And these are some of the things that are currently being worked on by research companies across the globe. So what is the reality as we move forward? I think the day of non-homogeneous laminations will become a thing of the past. And I think that's being driven by your major consumer groups. And, you know, I talked to one the other day and they said they have a goal. They don't want any polyester in their structures within 2 years. And it's all to do with this business about having non-homogeneous lamination. So this is what's coming. This is what you're going to be asked about. And there is no doubt it's being driven from a pretty high level within the industry. And to achieve what these companies want, there's going to have to be various coatings used, vacuum deposition technologies and new novel coatings. And also you're going to have to look at the fact that people are going to have to develop these new films. You know, a more heat stable polypropylene. Currently working with a polypropylene that's pretty well heat stable up to about 160 degrees centigrade. Typically it would be about 130 degrees and it would start distorting and shrinking and doing all those sorts of things. So people are working towards that. In addition, film producers will produce products, as I've said, to allow homogeneous laminations or monowebs. So, you know, your polyester guys, they're working hard at the moment to make a film that will give seal integrity and sealability on high-speed machines, so as that they can eliminate a polyolefin from a structure. And what I think I'm saying is, you're still going to have polyester in the market, but it will be for different applications. But the lamination won't be asymmetric; it will be homogeneous. And it's also going to be necessary, I believe, when these new films come along, that you have polymer identifiers that can facilitate automatic sorting. You know, one of the great things with polyester is, and polyester bottle and recycling, it's actually picked up electronically and sorted. But in reality, we can't sort all this film and by hand, because flexible packaging is small. And so some sort of identifier in the films that say, when something looks at it, this is polypropylene or this is polyethylene, I think is going to be necessary. And there are technologies out there that can actually do that. So that brings me to the end of my presentation. I hope you've enjoyed it, and thank you for listening. And I'll look forward to the questions related to this after Keith Damarell has given his presentation. Thank you.
Thank you very much, Stuart. Just to say to everybody, just to finish off Stuart's presentation there, Stuart, thank you so much for taking the time. I've heard people use the phrase innovation and renovation. Now, a lot of what Stuart's talking about, I know, is renovation. It's stuff that we've known and used about for many years, but the renovation here comes with this coating technology from that enables these really high barrier solutions. And I have to say, I've been looking at these barrier figures for quite some years, as I know a number of you have been. And some of the figures that Stuart's quoting here are game-changing, and the best option that we've ever seen in our industry to replacing foil, genuinely replacing foil consistently. So truly exciting, I have to say. And there are a couple of questions, one from Sarah, one from Stuart. We're going to come to those after Keith has done his presentation, if that's okay. So without further ado, I'm going to pass on to Keith Damarell. And Keith, if you wouldn't mind introducing yourself, of course. And I'll share my screen, which has got, of course, your presentation on. And just for everybody else on the call as well, if you do want to pose any questions, please do so in the chat box. We will come to those at the end. Over to you, Keith.
Yep, thanks, Liam. Hopefully everyone can hear me. Yeah, I think this is my Chris Whitty moment as well, because I'm going to be asking Liam to do the slides for me, so hopefully that'll work okay. So just a bit of an introduction. I'm the MD of a company called Sustainable Packaging Products Limited. It's a company focusing on the development and manufacture of barrier-coated papers and boards, which are targeting as alternatives to plastic packaging. So my background, as you heard earlier from Liam, is the paper industry. I work for companies such as the Wigan Street Paper Group, Sappi Paper Group, and Stora Enso, and more recently for the Harvey Group. So my background is technical, particularly in specialist coatings. So what I'm going to do now is I've got about 20-25 minutes to give you a synopsis of the coating methods used today for barrier coating on paper and board, and also talk a little bit about what can be achieved so far as alternatives to plastic-based materials. If we go on to slide 2, please, Liam, and I think you need to click this a couple of times, just to maybe 5 times to get everything up there. Yeah. I don't need to spend time talking to you about the need for barrier-coated papers and boards. Most people are aware of the legislative changes, consumer demand, and the CPG commitments for renewable and sustainable packaging by 2025. All I want to highlight here is that I'm going to be talking about paper-based packaging materials, and really the highlight here is that we're targeting sustainability or sustainable products as really meaning three main things. One is that those products will be conventionally repulpable. In other words, you can actually dispose of them in the normal waste paper stream, that they would be biodegradable. And that really means biodegradable either in aerobic conditions, anaerobic conditions, or even marine conditions. And then lastly, ideally made from renewable materials. Now, being paper-based, generally speaking, there is a renewable content with paper-based materials, at least sort of 95 to 98%, but the coatings we're using today are not all renewable, but there's a goal to transition those to become renewable as we go forward. So if we move to the next slide, please, Liam, and we talk about, what is the challenge? What we're really looking to do here is either replace chemicals that are considered to be not safe, particularly in terms of health and safety, or to remove materials that have a detrimental effect on the environment, like multi-layer plastics which you just heard Stewart talking about, that are not easy to recycle and are not biodegradable. Now, if we take a look at the barrier requirements, there's sort of a bit of a pyramid here where we start with the barrier requirements that are fairly minimal at the top and we work our way down. And we start with barrier requirements for things like food service, burger boxes, which require primarily just a grease barrier. Grease barriers today are or have been achieved using fluorocarbon chemistries. I think most people are aware these are considered bad active chemicals now. They're the forever chemicals. They're being progressively banned in many countries. Many states in the US now are banning these materials. So that is considered a bad active chemical, but it's just grease resistance. If we move down the pyramid, we start to move to products that require a higher level of barrier requirement. Things like burger wraps or bread wraps, where you need not just a grease resistance, but you also need some level of moisture resistance. You might also need some sort of release characteristics. And today, a lot of this is achieved by wax treatment of papers. Things like, I think most people know Warburton's bread wax is a wax paper. The issue here is not so much on food safety, although there are some concerns around some waxes, paraffin waxes particularly, but the main issue is that these materials are not repulpable. As we move down the list, we come to things like beverage cups. Here, we're starting to look at plastics. Beverage cups are made with paperboard that is extrusion coated with polyethylene. Minimum coat weight, something like 12 grams per square meter. So now we're looking at materials that are higher barrier functionality, grease, liquid water barrier, but also heat sealability. We continue down the list, we start to move to materials that have even higher barrier requirements, things like dry food pouches, where not only do we need the grease resistance, liquid water resistance, now we're looking at things like moisture vapor barrier and heat sealability. And here's where we start to move into the area of multi-layer plastics, as described by Stewart, which are more and more difficult to recycle. And then continuing down, even higher levels of barrier are required for long shelf life products that require an oxygen barrier, things like proteins, things like, let's say, nuts, that if they don't have an oxygen barrier will go rancid, or some packaging requirements where the gas flushing is required. And then lastly, at the bottom, we have liquid packaging, which sort of combines all of those barrier functionality requirements, but in addition, long-term extended liquid barrier and often light barrier. And these are often achieved via use of things like EVOH and foil, as Stewart was mentioning earlier. What that means is we have a range of applications that require ever increasing levels of barrier, depending on the end use application. These barriers require increasing levels of sophistication, which include transitioning down to the multi-layer plastics and the very high barrier films that you heard Stewart talking about earlier. And generally speaking, so the higher the barrier requirements, the less sustainable, essentially, the materials being used today are. If we move to the next slide, please, Liam. So I want to talk about what actually can be achieved today. And I'm going to start with what actually can be achieved on the paper machine today when we're making paper and board. So many paper machines today in the industry have coating capability with things like size press systems. You can see on the left-hand side there something like a puddle size press, or on the right-hand side you can see things like a film press coater. These are used today in paper making quite routinely to apply things like starches and synthetic waxes to achieve a level of water resistance to paper, so it doesn't all act like toilet paper essentially. And this is where often things like fluorocarbons are added today. These on-machine coating systems now today are being utilized to apply what is effectively water-based and often natural-based materials like engineered starches, sometimes some lattices and other vegetable oil technologies, and even to some extent polyvinyl alcohol, water-soluble materials, to achieve grease resistance and in some cases some levels of moisture resistance. So on machine today, you can produce alternatives to wax treatment and alternatives to fluorocarbon treatment. This has been scaled quite significantly, certainly in Europe. For brands like the McDonald's group, I think they eliminated waxes and fluorocarbons from their packaging in Europe probably up to 7 or 8 years ago. And again, it's not as far forward now in other parts of the world, for example, in the US, but it is happening. People are transitioning out of those bad actor chemicals, fluorocarbons, and away from waxes with on-machine solutions. The good news is they're all renewable, they're repulpable, they're compostable, and if they're on-machine, they are fairly economically competitive against the previously used fluorocarbons and waxes. But there can be some restrictions to what chemistries can be used on a paper machine. If you want to go to the next slide, please, Liam. And this restriction is really linked to drying. So on a paper machine, the drying is usually by contact against heated cylinders. Some paper machines may have some infrared dryers after the size press or the film press, but mainly the drying is done with the paper in contact with heated cylinders. As a consequence of that, when you want to use more polymeric style barrier materials to achieve higher barrier performance levels, you run the risk of those materials sticking to the cylinders. Now, though some paper machines have invested in special coating and drying systems, one example is Kotka Mills in Finland, most do not have that. And what that means is this essentially restricts most on paper machine solutions today to just being those fluorocarbon and wax replacement solutions. Anything else, you have to look to be doing things off the paper machine. You move to the next slide, please, Liam. So the main focus today, when you're looking at achieving high barriers, i.e. beyond just the grease and slight moisture barrier, i.e. where we're looking at really plastic replacement solutions, it's largely done with off-machine coaters using those polymeric-based coatings. And those coatings include things like synthetic lattices, acrylics, SPRs, and other newly developed materials. And although this is off-machine, paper mills are looking actively now to develop solutions to bring this as close to their paper machine as possible. But as a whole, it's largely done off-machine. If you click it one more time, please, Liam. The coating methods used today normally include some form of either rod application, blade, or curtain coating. Coating solids can be up to 50%, and coat weights that are normally applied for each of these coating heads is between 5 and 10 grams per square meter. And the key goal here is really fiber coverage of that paper with the barrier coating. And because often with rod and blade coating, we're actually applying coating and then metering off the excess, it tends to give you a slightly uneven coating. If you look at the top right-hand diagram, you see the effect of a blade coater. The metering essentially just meters off the coating, and you get thicker and thin layers over the peaks and troughs of the paper. As a consequence, most off-machine coating operations apply more than one coating. They usually have 2 coating heads. So the first coating head is then covered up by the second coating head, and that avoids things like pinholes in the coating. Other coating methods can include curtain coating. There's a simplistic diagram on the bottom left there. You can see a curtain coating where this is a direct layer coating. It's a contour coating method where the coating actually just follows the contours of the paper. As a consequence, you get a very uniform coating with just one application. So those are the main coating methods used today on off-machine coaters for barriers. If we move on to the next slide, there is a growing interest in actually achieving barrier coating on paper and board using printing methods. The off-machine coaters with rod or blade or curtain coating are fairly expensive, need a lot of investment. Printing methods are somewhat less expensive. So there's two main methods being utilized today, gravure and flexo. So gravure is a fairly simple process. You essentially have an etched roll with cells, picking up the coating and transferring it to the paper substrate. And often you would have several gravure coating heads in line to produce essentially a multi-layer coating. The coating weights that can be achieved with gravure are much lower than rod or blade or curtain, but because you can have multiple heads, you can build up the overall coating weight. Similarly, flexo is another process being used to coat papers and boards with barrier coatings. In a way, this is similar to the gravure. You have a pickup roll transfer into an analux roll, which is a roll with cells, and that transfers to a transfer roll, which transfers to the paper. But the flexo press offers, again, multi-layer coating essentially in one machine. Flexo presses now, certainly flexo press coating that I'm utilizing today has a central impression cylinder with 8 coating units, and then has additional separate third overprint units. So we can, in theory, apply up to 9 coatings. The benefit of the multi-layer coating is that you can obviously build coat weight to ensure you're not having pinholes, which is very useful. But the other benefit is you can change the coating chemistries. You can have a couple of coatings with one chemistry that gives certain barrier functionality, but maybe by itself would have other challenges in terms of tackiness or blocking. And then you can put additional coatings on top of that that don't have stickiness or blocking. So you can actually choose different chemistries to build up the overall performance you're looking for. So whichever method is used, whether it's the blade or rod or curtain coating, or in fact the press applied coatings, there is still a critical issue to manage, and that is drying. We go on to the next slide, please, Liam. So most polymeric materials used in barrier coating today are based on these sort of synthetic latex materials, and they all work in a similar way. Some may be combined with some pigments like talc or clay, but they will all work in a similar way. So after coating and after they've been metered, they essentially are on the surface of the substrate as a dispersion of individual particles. Now, as the water is dried off, the particles start to pack together. And there's a key requirement in barrier coating is you've got to start the drying process gently. You must avoid boiling the water in that drying process, because if you boil the water, it causes bubbles, and those bubbles causes pinholes. And if you have a pinhole, you lose the barrier functionality. So then after you've driven off the water, you then need to generate heat to coalesce and film form the coating. And then in fact, you need to apply cooling to cool down the coating to give you a final uniform resistant layer. And the cooling is important to prevent blocking. If you have a coating that's hot when you reel it up, it will stick and it will cause blocking in the roll. So drying is one of the key reasons why there are limitations for on-paper machine barrier coating solutions, but also why, to a certain extent, off-machine coating investments can be fairly high, because you need to have the extended drying capability and cooling capability to make the barrier coating work well. So to summarize, really, on paper machine, you can do the fluorocarbon and wax replacement pretty readily. Off machine, using polymerics, essentially you can use the rod, the blade, the curtain coating, or the print systems, but you have to be very careful that you have the drying systems in place as well. So that's a little bit about the sort of technical processes of what's being used today for barriers. We move on to the next slide, please, Liam. Talk about some of the applications that can be achieved today via barrier coating. And I'm not going to go through all these. I think the key point to make is all of these applications that are utilizing today barrier coatings on paper or board are all conventionally repulpable and compostable. With repulpability, we do that via, there's not so many defined standards. We tend to work with the Fiber Box Association standards, where you have standard energy repulping, and then you have to pass all the materials through a screen and have and achieve 80% fiber passing through a particular screen. So there's some specific standards that we utilize to prove conventional repulpability. So all are conventionally repulpable, all are compostable. Not all of them today are using renewable materials in the coatings, but as I said before, you know, they are paper-based, so generally speaking, they're between 95 and 98% renewable. And the goal is to be progressively moving those coatings to renewable materials. So what can be achieved today? If I start with the next slide, please, Liam. You know, I've already talked about food service packaging. This is really where I talked about the fluorocarbon and wax replacement. It's very feasible on paper machine, and to a degree, some of this has been done on press for a little while as well. We're targeting a grease resistance as measured by the old kit test of between 6 and 9, limited water resistance and quite limited moisture vapor resistance. Many mills are doing this in Europe today, but also many paper mills are looking to transition to this in the US today. And some board mills are also looking to do this sort of on-machine coating as well. It can be challenging if the paper machines don't have a size press or a film press, but this is fairly readily achievable today. Move on to the next slide. When we start to work towards other examples where we are looking really to replace polyethylene coated papers. Now, polyethylene coated papers have been widely used as liners for some corrugate containers, as well as laminated solid board products that are used for meat packaging and produce packaging. For meat packaging, the solid board usually consists of a 5-layer laminate, and the inside laminate previously has been using a PE coated paper. Here you can see some examples of barrier-coated liners. We can achieve very high grease resistance by the old method of kit 12 plus, and very high levels of water resistance. You know, we measure water resistance now with the COB test, but instead of a 60-second, we do it with 30 minutes, and we get values below 20 grams per square meter for 30 minutes. There's an image there of a barrier-coated liner paper produced as a solid board, which is used generally for meat packing. And you can see liquid water in there, and test there, it can hold that liquid water for over 4 days. So those are being produced and achieved today. If we move on to the next slide, you might have to click twice, Liam. That's coating a liner and then making a corrugate or a laminate board. You can also coat now directly onto folding carton materials to produce high barrier performance. Again, similar barrier functionality, high grease resistance, high water resistance, some levels of MVTR that can be made suitable then for hot and cold food, and essentially is replacing what is typically 12 grams of polyethylene that is today usually extruded onto a folding carton material. If you move on to the next slide, and one I think that'll be very familiar to most people is beverage cups. And it's true to say today there are several board mills with off-machine coating operations and one with on-machine that are today offering barrier-coated cup stock for the production of beverage cups. It's quite technically challenging because as not only do you need even greater liquid water barrier, you know, for cold beverage cup, it needs to hold water for at least 4 hours, and for a hot coffee cup, at least 30 minutes. But the material also must have very good heat seal properties to run well on a modern cup forming machine. The other issue is cost. The cost is also of concern as a premium, let's say above 10% on the actual cup, could be challenging for major brands that have a very high value spend on their beverage cups. So as a consequence, there is essentially has been and continues to be some general resistance by the market and the converter base, particularly slowing down transition to these materials because they are challenging to run and they are more expensive. But they are readily recyclable and compostable, and there's a steady progression away from polyethylene extruded cups to these barrier-coated cups because of their environmental position in terms of recyclability and compostability. If we move on to even, next slide please, Liam, even higher barrier applications, I've got a couple of examples. High barrier wraps, this is different to what I talked about earlier, like a burger wrap that just needs grease resistance. An example I put here is things like ice cream or straw overwrap, where you need to replace polyethylene extrusion coating papers again to get a grease resistance, but this time now to deliver very good moisture vapor transmission barrier. But also because a lot of these products are formed on a form, fill and seal or a flow wrap type machine, the materials need to be heat sealable. These materials are now being produced, very high grease resistance, good MVTR, heat sealable, and are being looked at and being used now with ice cream brands. And you see a picture there. A lot of people are aware of paper straws moving to be paper straws, and the little bendy straws that go on the side of a drinks carton, which is called an industrial straw. Those industrial paper straws are now transitioning to a paper overwrap with a good MVTR barrier. Again, why move to a paper straw if the overwrap is plastic? But the paper straws are very susceptible to moisture ingress because it decreases the strength of the straw, but also they tend to go moldy when you get moisture transition. So again, this is a good example of where a high barrier paper that is being produced today can replace plastics. And then the next slide, please, Liam. Finally, I come to the even higher barrier materials, and some of these are sort of analogous to the ones that Stewart was talking about. And just a couple of examples here. Higher barrier materials where you need not just the grease, the water, the MVTR barrier, but you really need oxygen barrier or gas barrier. The oxygen barrier is really needed when you want long shelf life for proteins, where they would go rancid if they're exposed to oxygen, or for materials that are gas flush to extend shelf life. There are now paper-based materials available today that can be used as viable alternatives to multi-layer plastics. They offer heat sealability, so they work through a flow wrap and form, fill and seal packing lines, and they do provide that good shelf life performance. A couple of examples I put here, even things like tracing paper. Tracing paper, which is a really interesting material, has in itself a natural oxygen barrier. And you combine that with the barrier coatings to give grease, well, it already has grease, but to give moisture vapor barrier and liquid water barrier, you end up with a very interesting high barrier material. So paper-based materials do exist today for flow wrap, for pouches. Similar material, because they're heat sealable, will work well as lidding materials as well. And they do provide alternatives to multi-layer plastics. So they are fairly new, and therefore people are less aware of what's out there, and they are more challenging to run on those form, fill and seal and flow wrap machines. But there is a lot of work being done to develop further materials with higher strength characteristics to run better and even higher barrier functionality. So I come to the last slide. If we can just change slide, please, Liam. Back to my pyramid. It's only half changed according to my screen. You want to try that again, Liam? So technically, we have a very broad range of packaging material requirements, but they can be met today by barrier coated papers and boards that are all conventionally repulpable and compostable. Most are being met off paper machine coating, but that is probably going to change as the paper mills invest further. The manufacturing base for these materials is still quite small, but it's growing fast. The market awareness is still somewhat limited, and the economics are sometimes challenging. But with legislation and with packaging waste taxes combined with higher volumes, we'll see the economics getting better and better. And with an increased manufacturing base, these materials will move away from being what essentially maybe niche solutions today to mainstream solutions. The coating materials used today are still mainly fossil fuel based, like synthetic lattices, but there is a lot of effort being put into developing renewable based solutions for the future by some of the big polymer groups. I'm working direct with some of those. So although we're looking at renewable contents of 95 to 98%, it's highly likely within the next 2 or 3 years that will transition to very close to 100%. And the one thing we don't have yet, at least I'm not aware of it, is a good solution for that is repulpable and compostable is liquid packaging. But I'm sure in due course we'll achieve that as well. Okay, well, thank you very much for listening. That completes my presentation. I look forward to any questions that people may have. And feel free to contact me separately if anybody has any questions after the webinar.
Yeah, so just to come in there, thank you so much, Keith. I was particularly looking forward to your presentation, and it didn't disappoint, I have to say. I think your comments about people's awareness, at least my awareness of what was in the market for coated papers, was somewhat lacking. That was truly an excellent presentation. Thank you so much. I've been encouraging you, of course, to pose questions. I've got a couple for yourself, Stuart, so if you wouldn't mind unmuting yourself. And then actually, Keith, Damarell, afterwards, if you wouldn't mind, I've got a couple of questions from myself personally. So, Stuart, first question from you, from Sarah Greenwood. What are the pros and cons, if I try that again, of using these barrier technologies on PE? So processing temperature, these could be recyclable under today's guidelines. So is there much, are there many examples of PE being used for the vacuum deposition coated materials?
Yeah, there are some examples of PE having coatings. You know, one of the things that's happened is that in the newer pieces of equipment, that the heat retained by the film is very much lower. The heat exchange on the contact drum is very much better. It is more challenging, you know, because as a film becomes less firmly stable, then it becomes more of a challenge. But there are people that are metallizing polyethylene and cast polyethylene today.
Okay, thank you very much indeed. And the second question there from Stewart Patry. Maybe I can help with this one a little bit there, Stewart, but Stewart Patry is asking, what are the cost differentials for moving from a standard laminate to a vacuum deposition coated film?
My expectations, and you can probably back this up, Liam, if you look at that structure that I gave you, where we moved from the foil structure to the two-layer with the barrier coating, there are not as many operations involved, so immediately that reduces cost, and the amount of material involved is a reduction in cost. And as I said during my presentation, when you're using foil, you're at the vagaries of what the commodity is in the marketplace, and every so often people have a drive to get out of foil because of that, not just because it's recyclable. So I would say there'll probably be at least cost equal, and in many cases cost preferential.
Yeah, and just to add to that, for those of you who don't know, I work and co-own Benchmark Consulting, where we do these cost scenarios, this cost benchmarking on these new types of scenarios, and really mirroring a lot of Keith Damarell's statements to do with availability and volume in the market. There aren't that many producers of some of these technologies that we're talking about, both, as Keith mentioned, on the coated paper side, but particularly I know personally on the vacuum deposition coated films. And the issue with that availability, of course, it does push up the price, but also, you know, standardization of materials. So, you know, looking at the people that have participated in today's webinar, and thank you to all of you who have attended again, the more of us that push these solutions forward, the bigger the volumes are going to be. And then, you know, what we're talking about today as hugely innovative structures then become the standard, one hopes. And then we can really start making a change. So thank you.
Can I just add something as well, just to emphasize that? In my discussion with Nick Copeland, who's R&D director at Bob's Vacuum Technologies, I think that's near enough for his term.
Yeah,
they are actually sold out on equipment that they have to supply in this coming year, so they can take no more orders. So that's probably a fair indication that the demand for this equipment and the demand for this technology is increasing rapidly.
Yeah, that's a good comment. And Keith Damarell, if you wouldn't mind unmuting yourself, I did have a couple of questions from my side. The coated paper side, when I do cost benchmarking, often I find I mean, plastics are not cheap. The processing technology, flexogravure, some of the things you're talking about are very similar to that which are deployed in the flexible packaging side. Puncture resistance of some of the papers, with some of the applications you're talking about, puncture resistance is quite important. Obviously, paper can be, it's got quite a lot of low tear resistance. What sort of grammage of paper are you talking of using for some of the pouch applications and things like that?
So it's a good question, because one of the early challenges, and still challenges today, is runnability on flow wrap and form film seal, because of the strength characteristics of paper substrates. And then when you have the contents inside, then you have an issue around the puncture resistance. Typically, we're running papers as low as 70 GSM for the pouch application, depending on how big the pouch is or what weight of product is going to go inside. However, to your point, there are what we call standard papers that are standard strengths. I personally am working with some very new developed papers that are extremely high strength papers, very high tensile tear and fairly high stretch property papers that essentially almost, I wouldn't call them unbreakable, but they're extremely strong. And then pouch papers made with these new high strength papers. In fact, I first worked on it to try and solve a problem for toy packaging. Because toy packaging, Lego and things like that tend to be very aggressive and puncture through the paper substrate. So that's where I started. But these high strength substrates are working well for the machinery, and then for some of the more challenging contents that will be sort of hard edge contents. But I think that's why there's also a learning curve for the OEMs. You got the process machinery people have to learn a little bit more about how to be more adaptable to running paper substrates, because generally speaking, they're just set up to run plastics with the high strength and the stretch characteristics. So there's a bit of both. Some OEM support would be useful to facilitate the use of paper-based substrates for the future.
No, that's fascinating. I can't even begin to tell you. And you mentioned machinability as well. The only other question that I had was to do with sealing through contamination. I know a lot of the names that are on this call, and I know a lot of us have had our times crawling around vertical and horizontal form, fill and seal machines, trying to get our solutions working and damaging what are otherwise very expensive suits in the process. Sealing through contamination for some of the product areas that you're talking about, if you want to talk about nuts and the salts and fats that go in there, these coatings, do they seal through contamination quite well as well?
Yeah, I have to say, I'm not an expert on, on sealing through a contamination, but I can tell you that's largely linked to the amount of coating you have there, the coat weight. So sometimes you don't need the higher coat weights to get the barrier functionality, but you need a higher coat weight to give robustness for sealing through contamination. So, yes, the simple answer is yes, they will. But to achieve that, you have to put a slightly higher coat weight. It's really the amount of material you've got there that can flow together under that heating environment. And then it'll be the same as plastic. It'll perform as good as plastic materials.
No, fully understand. Really, really interesting. Sorry, this is becoming a conversation between myself and Keith. So is there anybody else that would like to ask either Keith or Stuart a question whilst we're on? If you'd like to either type something in the notes box, or at this stage, if you want to unmute yourself, you're more than welcome to jump in as well. But in the absence of any further questions, I am going to thank our presenters again, Stuart and Keith. Both Stuart and Keith have obviously given me permission to pass on their details should you wish to get in contact. I know Stuart's actively working on several very, very interesting development projects on some of these technologies that he's discussing. So again, if you need support on any of these, I think the key message is, yes, these are innovative structures, both on the coated paper side and the coated plastic side that we've been discussing today. But it's really incumbent on us all to try and push these forward, to take them from being an innovative solution to a commodity solution, such that, really we can make a difference to the sustainability of the packaging that's out in the market. So the presentations will be made available. We will probably post those up on the IOM3 website, or maybe in a Dropbox location. So we'll send you those links. But other than that, I do have one other question here from Jeremy Gallagher. Are you aware of any developments for papers? So this would be a question for you, Keith. Are you aware of any developments for papers with water-based barrier coatings plus extruded poly sealants to add barrier plus durability? So we're talking about almost both solutions that you were discussing here, Keith.
Yeah, I mean, the simple answer is yes. There are some extrudable materials, some of them based around polyvinyl alcohol type materials that in themselves give very good oxygen barrier, but they have very little water or moisture vapor barrier. So there is work being done combining water-based dispersion barrier coated materials with those extrusion materials to produce a final product that has all the characteristics you need. And a lot of the work being done today is in fact combining one or two different materials together to get the final product performance that's required.
Excellent. Thank you very much indeed. Yeah, hugely interesting area. And as you said, Keith, by the sounds of it, most of these solutions that you're talking about are more or less, say, readily available, probably need some developing for specific applications, but at least the the basis of these innovations are there, which is nothing short of impressive, really, given that we weren't talking about these if we go back 2 or 3 years. So any other questions before we close off the session? I'm aware we are more or less 10 minutes over now, so thank you to our presenters for staying on for an extra 10 minutes. Anybody else? Okay, I'm going to close the session off there. I'm going to say thank you. Oh, Ian, you're waving at me, and Keith Barnes is waving at me. Ian, would you like to unmute yourself?
Oh, I thought.
Oh, you have unmuted yourself. Yes.
I am unmuted. Oh, jolly good. Sorry, all I wanted to just sort of wrap up things with is to say thank you to Stewart and obviously to Keith for doing such a tremendous job, but also thank you, Liam, for being master of ceremonies today.
Yeah, thank you.
It's a really important job, from an East Midlands Packaging Society perspective. Hopefully, we've done our job today. We've given a lot of information to a lot of people. According to the list, we've had over 60 people join the conversation, which is great. I think it's probably the most we've had on a webinar. So hopefully we can continue. And on that point, the thing I just wanted to say was next month we are going to be helping our colleagues in North of England Packaging Society, because they've got a webinar on the 3rd of February. They've got, I've got to remember now, Ian Schofield, a lady called Olga, whose name just escapes me, her surname, Olga Munro from Leeds, and Rob Thompson. So they've got a webinar on that lunchtime, 3rd of February. And then we've got another webinar on the challenges of recycling PET bottles. And there's a gentleman called Ahmed Detta from a company called Enviru, who's looking to set up a business in the northwest of England. And he's going to talk about the issues that, he's looking at to overcome to actually get more PET actually into the recycling stream.
And by the way, just sorry to jump in there, Ian, that webinar might sound a wee bit dull, stuff that you've heard many times over. Ahmed Detta is a close personal friend of mine, and the business he's setting up is a lot more than just a polyester recycling plant. Highly recommend you join that webinar. It's a pretty special business that he's setting up there. So
yeah, well, we'll send information to everybody in the coming days and weeks. So okay. Thank you again.
Do you mind if I bring Keith Barnes in? Keith, did you want to put a question forward, or are you all good there? It's all right, Keith. I'll unmute you. No, I can't unmute you. Keith, you're going to have to work out the unmute button there, mate. Nope. Nope. No. No. No.
That's it.
There we go. Hello, Keith.
Should be able to talk now. Yes. Well, I can only repeat what Ian said. Very interesting to learn these forthcoming activities within coating, and like all areas of packaging, there is a vast impetus of innovation and research and development going on in every area. We have to do this to combat climate change and to help with the problems that will occur after COVID is over, whenever that may be, and let's hope it's pretty soon, because I'm getting bored staying at home, and I'm sure everybody would agree with that. There are many things coming on, and I hope that those people who have been attending follow the IOM3 website, because there are other webinars coming up from other divisions of IOM3 that are equally interesting and worthy of spending an hour listening to. So again, congratulations to both of the speakers. Thank you very much, and thank you everybody for attending.
Yeah,
my pleasure, Keith, and thanks for the compliment.
No, cheers, and thanks again to Stuart and Keith. I'm going to end the session there. I'm conscious that we're now 15 minutes over, but thanks to everybody for attending, and hope to see you on the next webinar. Have a good rest of the day. Bye now.
Cheers.